First of all, I'm Roger, Kilo Mike 4, Lima Hotel Zulu. I had hoped that my collaborator, Steve Narden, would be able to log in as well. We knew when we accepted this date that Steve might have a conflict, and a schedule conflict, and he thought he could work around it, but wasn't able to. But Steve's role in this area will become apparent as I give my presentation. I'll mention that Steve works at Regal Beloit in Fort Wayne, Indiana. Regal, for short, is one of the leading manufacturers of high-efficiency DC motors. And the reason I'm interested in Regal's products is the motor for the blower in my furnace was manufactured by Regal. And when I started having RFI problems, as I'll explain, I was put in touch with Steve. Steve is a ham also and an amateur extra, and was working full-time as the RFI lead at Regal, has now retired but is still working part-time and trying to train a couple of his successors. So he's quite a resource. Out of fairness to the competitors, I should say that there are many different manufacturers that make high-efficiency DC motors, and I'll explain why they're important in a minute. But I'm interested in this particular brand because it's what I have, but I certainly don't mean to slight other manufacturers. It was almost 4 years ago that I gave my original presentation on this topic, October 2nd, 2017, and some of you are probably wondering why I'm going to bore everybody with the same ideas again. Well, so what's new? Well, a number of things. First of all, although the current presentation is rather dense, I've got about 70 slides, and some of them are fairly full. It's intended as a handout, and it will be posted on the club website shortly after I finish this presentation. And it's also designed to be emailed to people that might be having an interest in this area, have similar problems. A few very basic acronyms. I use A/C for air conditioner. Some people use lowercase a, lowercase c. AC or DC, obvious meanings, alternating or direct current. And ECM stands for electronic commutatorless motor. It's sometimes mis-expanded, the acronym, for electronic controlled motor. That is not the case. So what is new? Well, first of all, I made more careful measurements after my original presentation. I discovered I had more severe issues than I thought, and I've added multiple measures that resulted in additional mitigation of the RFI I was getting from my own HVAC system. I've also improved the screenshots rather than just using a camera to photograph the scope of my IC7300. I learned how to capture the screenshots to a microcard. And finally, one of the big motivations was after the YouTube presentation went online, a surprising number of other hams wrote to me telling me that they had similar problems. And I began writing back with individual letters and individual PowerPoint extracts. And I finally realized it would make a lot of sense to do an updated presentation that could be submitted to anybody. I'm going to ask people as we go to reserve your verbal questions until the end, but by all means, put questions into the chat box. I hope to be done with less than an hour and have plenty of time to answer your questions. If you have a question on a particular slide, every slide has a page number in the lower right-hand corner. And if you put your question in with that page number, I'll know exactly which slide to go back to. Furthermore, if you just feel you would like to spend more time discussing a particular slide, just put the page number down with a question mark, and we'll get back to it later. So that is kind of why we're doing this and how I hope to present. Now here's the order of presentation to give you a miniature preview. We're going to discuss briefly what RFI, radio frequency, and EMI, electromagnetic interference, are. Then we kind of get to the heart of the new laws. There are new efficiency regulations which dictate the use of high-efficiency DC motors in furnaces. And these motors are likely, relative to the older induction motors, split capacitor motors, for example, to cause RFI. And we're going to have to learn to deal with that, we, the ham community. Then I'm going to talk about what an ECM is and why underneath the hood you have a relatively high frequency pulse width modulation oscillator. And that is what's creating the RFI and the harmonics. Next, I'm going to talk very briefly about HVAC terminology, how furnaces and AC units work at a very high level, and clarify some nomenclature. The reason I want to clarify the nomenclature is if anybody wishes to shop or install a new HVAC system, it really helps to understand the jargon used. I didn't when I bought mine, and that might have created some of my problems. Finally, I'll finish up well. Fourth, I'm going to do a case study in RFI mitigation on my own system, illustrated with screenshots and pictures of the filters and ferrite chokes that I've used. Then I'm going to offer about 4 pages of suggestions about what to look for when you, a ham radio operator, is seeking to upgrade your air conditioning or heating system, or perhaps buying an entire new system. I was hoping Bill Mims would be here because he and I had some email exchange a while back about what to look for. I'll have to make sure he gets a copy of this briefing. Finally, there are maybe 3 or 4 tropes or cliches about RFIs that I'd like to address, a few final facts, and finally, some brief additional case histories, which are just 1 or 2 page summaries of people that I've worked with via the internet, or that Steve has worked with, or that both of us have worked with. I probably won't go into the appendix, but that depends how much time we have left. Okay, I'd like to mention some references up front. Everybody puts the references at the end, and everybody's fallen asleep by the end of the presentation, so everybody misses the references. The ARL RFI book was edited by W1MG, Mike Gruber, who has since retired from the ARRL. But there is a replacement who also works at the ARRL laboratory and can answer questions about RFI. One deficiency is there's no chapter on RFI from HVAC systems. The other book I'd like to mention, I haven't read all of it. I've read some excerpts. It's by Henry Ott. And this is something that Steve pointed me to. He says it's absolutely the best standard textbook on electromagnetic compatibility and controlling RFI problems. Now, Henry Ott's company closed, but his website is still up. And on his website, you can find 3 very good very short PDFs called Dipoles for Dummies. And they explain how in any system, electromagnetic system rather, you will often have components that are capacitively coupled and inadvertently, without your knowledge, form a dipole, which can then be a source for RFI. So EMI and RFI are used interchangeably here. EMI is any frequency of electrical noise. RFI is a specific subset of electrical noise on the radio frequency spectrum. Conducted EMI is electromagnetic energy that is propagated along a conductor. And typically conductors such as house wiring act as an antenna to radiate the RF energy. And conducted EMI is primarily an RFI issue at frequencies below 30 megahertz, which of course is the wheelhouse for most of our ham radio operations. Radiated EMI is electromagnetic energy that's directly radiated by the source device. It's primarily an issue at frequencies below 30 megahertz also. And above 30 megahertz rather, Inductive coupling is a path with interference from a source device coupled into the victim device by a magnetic field. It's usually a very low frequency phenomena with a very short propagation path. Mike Gruber, by the way, helped me develop these last through view graphs and clarified some of my thinking about the different flavors of EMI. Now we get to the law. This is a busy view graph, but it's an important one. After July 3rd, 2019, all gas and electric furnaces must use more electrically efficient fan motors, which have an average efficiency of 46% above the previous baseline. I know there are people in here that love to read specifications, so after the second bullet, I put the specification for this massive document, which is online. But I've also excerpted what I think are the main points, so nobody else has to actually read this unless they want to. The efficiency units are in watts per cubic foot per minute of airflow. That's what watts per CFM stands for. And so specific technologies weren't really mandated, but if you look at the footnote in the lower right-hand corner, the Department of Energy did not screen out, was the way they phrased it, did not screen out the following 4 technology options: inverter-driven PSC fan motors, which I'm going to talk about, high-efficiency fan motors, which I'm also going to talk about, multi-stage heating controls, that will come up, and backward-inclined impellers. I have no idea what that means. Now, ECMs are available for air conditioning systems also, but are not mandated. AC systems often use variable frequency drives, which drive AC 3-phase compressor motors. It turns out that variable frequency drives have exactly the same problem that ECMs have, and I'm going to explain what it is. ECMs have pros and cons. I have one in my furnace. It's more efficient airflow, more even heating capacity. The speed is adjustable from high to low. You can adjust the torque and the frequency. However, frequently there's more RFI, and that is now our problem. And I say it is a mandated problem because it's very difficult to buy a new furnace which does not have an ECM motor. HVAC people sometimes call this law the HVAC mandate, which is not really true, but in practice, that's what it's turned out to be. Almost everybody manufacturing furnaces is now using an ECM from one manufacturer or another to drive the blower in the motor. So what is an ECM? It's actually a somewhat old idea. General Electric developed ECMs in 1987. It stands for electronically commutated motors. For those of you that are familiar with induction motors and earlier motors, it's a brushless DC motor. It's a permanent magnet synchronous motor. By a brushless DC motor, I mean there is no physical computation of the direction of the current in the stator. By synchronous, I mean the rotor is synchronized with a rotating magnetic stator field, and I'm going to present graphical examples of that. There's no rotor slip, and it's more efficient, probably 65 to 75% efficiency than an induction motor, which, based on what I've read, has about 45% efficiency. The blower motors for ECMs are usually 3-phase DC, not 3-phase AC, which most EEs are familiar with, but 3-phase DC. And the motor control unit, which is always uses a microprocessor, can either be incorporated into an ECM or it can be a separate unit with a wire harness or cable leading to the controller. So basically you have, in the case of mine and others, 120-phase single AC in, 3-phase DC out to the motor. The microprocessor controls the 3-phase DC voltage and current, and the motor has variable frequency speeds. So what are these and how do they work and why are they problematic? This is a diagram actually from the ECM textbook, which is freely available online if you want to know a lot more about ECMs than you need to know. but I want to point out a couple of things. There is a control unit, which in this case is part of the ECM. There is the stator, which does not rotate and has a large group of coils around the circumference. And there's a permanent magnet rotor. If you're familiar with induction motors, you'll notice there are no coils on the rotor because it's not an induction motor. It's permanent magnet motor. There are permanent magnets laid out, and they alternate in orientation, north-south, south-north, north-south. And as the magnetic field rotates around this circle of coils, the permanent magnetic rotor tracks that rotation and remains synchronous with it. This is an ECM3, which I again have to have my furnace, a Regal Beloit ECM3, and that's why I'm particularly interested in it. The ECM3 has a fixed frequency 18 kilohertz pulse width modulator, and I'm going to show you what pulse width modulation is in a minute. And it varies the phase switching speed from about 300 RPM to 1200 RPM, although there are some motors that can run up to 1800 RPM. For those of you that are familiar with motor theory, the legacy motors have 18 poles. The newer sine drive motors that Regal produces, sine drive motors, have 12 poles. Now let's talk about how this works, and then we'll talk about mitigation. This may be the most important slide in the deck with respect to understanding why ECMs are problematic. ECMs use pulse width modulation to modulate the DC voltage output, the triphasic DC voltage output, as a complex of time. The frequency of the pulse train is fixed. Regal uses 18 kilohertz pulse width modulation. I'll give some other numbers for other devices later on. The reason the average voltage varies is because the duration of each pulse changes, and not because the amplitude of the pulse changes. So you can see I have a constant input voltage, and but the frequency changes, and rather the average pulse duration changes. And over this segment, the right-hand segment, you would get a higher voltage, and over the left-hand segment, you would get a lower average voltage. So lower average voltage, higher average voltage. But in all cases, you have a pulse train frequency of 18 kilohertz. And that's the problem, because if you have a square wave, you have harmonics. If you had a perfect square wave, you would have harmonics at all the odd frequencies. I have no idea what the spectrum looks like for a pulse width modulation unit, but I can tell you from experience that it can produce significant harmonics. These two are probably the busiest slides, and I'm not going to try to explain them in complete detail. But again, I think it helps if you're trying to understand these problems to have some idea how these motors work. This is a hypothetical motor. It has 3 different magnetic poles. And as these coils are activated by the microprocessor, which determines which coil is being activated and what the temporal pattern is of the currents going through the coils, the magnetic field rotates around the stator, and the rotor, which has fixed magnets, tracks the magnetic field. And this is a very elegant arrangement because you can change the speed, and you can change the speed easily just by increasing or decreasing the size of the steps between these pulses. And what I've shown here is the hypothetical voltages in the 3 coils as a function of time across the course of one complete rotation. From here to here, the rotor rotates 360 degrees. During that time, red shows the currents in the red pair of coils. You have a positive pole and a negative pole. Green in the green pair of coils, and blue in the blue pair of coils. And so you have what are called 6 commutation phases. In effect, the rotor rotates through 6 different positions of the magnetic field. The positions of the magnetic field are also shown in the table in the bottom right. Well, the green is positive, negative, or off during commutation phase 1. Green is positive, red is negative, blue is off. During the second position of the rotor, the green coil is activated, the red coil is off, and the blue coil is negative. And this shows the torque, which you may see theoretical moment of torque, which has a bit of ripple in it. I'm going to go back to that point. But this is how ECMs work. And what I've shown schematically here is that each of these continuous levels of current is actually generated by chopping at 18 kilohertz per minute. This is another way of looking. Well, this is actually a different device, and it's the one found commonly in air conditioners. This is what's called the 3-phase trapezoidal frequency. This is called a trap drive. You have AC, a single 120 volts or 240 volts coming in. You convert the voltage to a 3-phase commutation sequence. The microprocessor specifies the current for the torque and the RPM with constant feedback. And this is just a graphical representation of what I showed on the previous page. This chart and this chart are one and the same. This shows you have a trapezoidal waveform, B, A, and C, in the coils I showed. And it's called a trap drive. There are also sine drives in which, rather than being a trapezoidal waveform, you get a sinusoidal waveform. But the main point, again, is that these waveforms are generated by pulse width modulation. You have a constant oscillator operating at, in this case, 18 kilohertz. And this creates a lot of harmonics. So let's talk now about what's in a very basic, high-level abstraction of an air conditioner. Question is, why am I talking about this now? And the reason is that it's important to understand that in a new system that you might buy, there can be 3 or 4 ECMs, all of them as potential sources for RFI. Actually, the compressor is often driven by what's called a variable speed drive or a variable frequency drive, but this also uses pulse width modulation, and it also has a variable speed pulse width, has a variable speed oscillator operating at some fixed rate under the hood, and it can also be a major source of RFI, as mine is. So in the diagram above, you can see that you have a condensing coil and a fan, both of which are outdoors. The condensing fan motor may be an ECM, or it may not. You have an expansion valve, which doesn't concern us. The blower in the furnace is 3, and it's blowing over a coil of compressed cold fluid and evaporating it, which is why you get cold air indoors. And the compressor may be a variable speed drive, which is outdoors. And the compressor, if it is a variable speed drive, may also be a source of RFI. So there was a Lennox field engineer I was friends with, and he said, as of a couple of years ago, particularly in commercial systems, it was not unusual to find 4 ECMs, direct drive DC motors, or 3 ECMs, and a variable speed drive, which is almost the same thing, except it produces tri-phase output, tri-phase AC output, rather than tri-phase DC output. And all 4 motors can be significant sources of RFI. My friend isn't with Lennox anymore. I don't know whether he retired or just gave up. Maybe both. So I want to go over some common terminology used in HVAC systems. And again, the reason I do that is I am want to talk about some guidelines in buying a new system. I don't want to dwell on it, but if you're going to talk to somebody outlining different options, you need to understand these terms. PSC motor is just a permanent split capacity motor. Split capacitor motor, it's an induction motor, usually has 3 fixed speeds, no RFI, but because of the new regulations, PSC motors have been replaced by ECMs by mandate for the furnace blower motor. So somebody asked me, well, could I get a furnace with a PSC motor? And the answer is, these days, I think it's unlikely, but I suppose you could ask. Now, a 2-stage gas furnace is a gas furnace where you have both low and high flame settings. I have one. It's relatively efficient. But a 2-stage gas furnace may also have an ECM blower motor. So if somebody tells you this is a 2-stage gas furnace, and I guarantee it won't have any RFI, the question is, really? Does it not have an ECM blower motor based on the fan efficiency regulations of 2019? The salesman may lose the sale at that point, but that's the question you ask. A 2-stage dual-stage air conditioner is an entirely different matter. That means it has a 2-speed air compressor with high speed and low speed. It has some of the advantages of a full variable speed compressor, but without a variable speed drive, that can be a source of RFI. And remember, a variable speed drive is almost the same as a ECM. It's just it produces 3-phase AC rather than 3-phase DC. By the way, the air conditioner will also have a condenser fan. And according to my contacts at Lennox, the condenser fan may be an ECM. If you're wondering why ECMs are being put into air conditioners and elsewhere, the answer is people want high efficiency, particularly in commercial settings, and may not have to worry about RFI, but we do. I've been talking about DC inverters, which I'll just go over briefly. It's just a device. It's sometimes called the DC inverter. The whole unit may be called an inverter. It's also called a variable frequency drive and a variable speed drive. I'll go back to those terms later. In my external AC unit, I have a compressor manufactured by LG, and it has a variable frequency drive. It's the source of major AC RFI. According to my Lennox contact, the 3-phase outputs vary from 3 kilohertz to 9 kilohertz per phase. And what it consists of is a converter that converts AC to DC, a smoothing capacitive filter bank, a control unit that uses, guess what, pulse width modulation to convert the DC output to 3-phase AC power for the compressor motor. And then finally, most AC units have 3-phase AC induction compressor motors. They don't have DC motors, but the damage is being done by the inverter, which uses pulse width modulation. And by turning out, by giving you 3-phase AC, the pulse width modulator can vary the amplitude of the 3-phase AC, which in turn varies the speed of the compressor motor. So the good news about inverters is you have a AC compressor which has almost continuous range of speeds, and that makes it very efficient if you're trying to adjust the speed to how hot or cold it is. The bad news is there's a pulse width modulator under the hood creating lots of harmonics, potentially creating lots of harmonics. LG said their inverter was within specification, but that wasn't helpful in solving my problem, and I'm going to explain what I did. Because if you have and just to repeat the last point, if you have an alternating current 3-phase motor, the only way to change the speed reliably and efficiency is to alter the efficiency of the power applied to the motor, the frequency of the power applied to the motor, to something other than 60 hertz. And that requires pulse width modulated to generate the appropriate waveforms. Now, at this point, you may be confused, but I hope people take away a simple message. ECMs are almost mandated in furnaces. Variable frequency drivers are an option in most air conditioners. An inverter is just a synonym for a complete integrated system in an air conditioner, which has a variable frequency drive and usually a 3-phase AC motor. If you're wondering what the difference is, there's an excellent explanation on this website. The take-home lesson is that all of the above generally use pulse width modulation and are potential sources of RFI. Now, I'm sure, like most other people in the club, practically everyone has taken their furnace apart. I've done it 3 or 4 times now to try out different mechanisms for reducing the RFI from the ECM, the fan blower assembly. The ECM is actually contained in that barrel at the bottom on the right. It's not visible here. It's variable speed and provides constant airflow. There's an integrated control board for it. This is a Lennox gas furnace. It's relatively new. You'll notice there's one other fan which is present in all furnaces. It's called a draft inducer. It clears the gas, toxic gas, out of the furnace between heating cycles. And it also pressurizes the furnace, and the combustion air pressure switch should be activated at that point. If the draft inducer pressurizes the furnace and the combustion air pressure switch on the left does not close, there's a leak in the furnace and the furnace should not turn on. So inside of this barrel, there's the ECM3 motor. I showed a picture of that earlier, and I'm going to talk about it some more. So the very first case study on EMI reduction is KM4LHZ. That's me. I have an ICOM 7300. At that time, I had a 63-foot end-fed antenna. And I installed a Lennox gas furnace and an XC25 external AC in September 2014. There was definitely RFI. The fan assembly in the furnace is a Regal Genteq ECM 30. And that's where Steve's expertise comes in, because he's the RFI specialist for Regal. And I solved the RFI problem first by installing a filter which Steve designed and which I'll show you in a minute, and second by adding a ferrite choke which I designed and which I'll also show you. And there was a significant reduction in RFI from the furnace. The AC configuration has an LG variable capacity inverter-based compressor, that's a mouthful, and an EMB PAPS ECM condenser fan motor. When the service techs were diagnosing my problems, because they came out under terms of the warranty and examined my system and isolated the source of the RFI, they said there were no problems at all with the condenser fan motor, but they told me I definitely had an inverter problem. And I had no idea what they were talking about. I was ready to reach for Google Translate by the end of that conversation. But I found out what an inverter is. And it converts, as I said, single phase AC to triple phase variable frequency AC to drive a variable frequency compressor motor. My local service dealer called up Lennox. Lennox sent out a field engineer, came out twice. This is after we had solved the above problems, or while we were solving the above problems. The dealer also installed what I call the Regal ECM filter, which I'll show you in a minute. And I subsequently took my furnace apart and added a ferrite choke. As far as the AC went, the dealer concluded that there were 7 lines for the thermostat control, and the installation instructions recommend tying off the unused lines, which the field engineer did. That didn't have much effect. Then he added a ferrite choke, which reduced the RFI further. Subsequently, more or less working on my own, I figured out a way to put in a low-pass common mode filter, and that resulted in a significant reduction in AC RFI, and that's where I'm at today. And I'm going to show you what all these things, I'm going to show you pictures of the RFI as seen on the screen, what the filters look like, and how they were installed. This is RFI from the original fan blower motor during the heat cycle. With no EMI filtering, I was at roughly the frequency at which the world's most boring net is held. And you can see I was getting nowhere fast because I had these massive RFI lines roughly every 17 cycles. There was also a bit of noise that occurs right here when the furnace is powered on before the blower starts up. I think that might be noise from the draft inducer, or it might be noise from the pilot light itself. I have no idea. And here, all I've done is raise the spectrum threshold, which makes weak signals stronger. That's diagram B in the upper right. You can see the interference lines very clearly. The next picture I took by, I think, having my wife stand by the furnace and turn it off. And you can see the waterfall is rising. And during furnace shutdown, right here, all the noise goes away. And after furnace shutdown, there's whatever noise is left is not attributable to the furnace. So this is where I started. And after the technician from my local dealer analyzed this problem, he concluded it was arising from the furnace blower. He sent somebody from field engineering out. Field engineering put me in touch with Steve Narden and out at Regal, because Regal manufactured the blower motor. Steve provided me with a filter, which I'm about to show you. And we've been working together ever since on this problem and helping other people and on some improvements to the original filter. So this is just another pretty picture, because I try to keep things a little bit concrete so everyone doesn't go to sleep. In my furnace, there's a squirrel cage blower fan. At the end of it, this is my sketch, by the way. I should have subcontracted to Brownie Locks. At the base of the blower fan, there's the ECM3 Regal blower motor. And right here, you can see that the blower motor just barely sticks out of this barrel, which contains the blower fan. This is a picture that Steve provided me with. This shows the head of the motor. The body of the motor driving the blower fan is inside the cage. And this shows the filter that he plugged in to the power port. And he provided me with such a filter, and the dealer came out and installed it for me. And I'm going to spend a few minutes explaining how this filter works, because it's actually rather simple. This is a capacitor. This is a schematic which Steve was kind enough to provide me with. It shows the connections between the filter and the 5 AC and the 5 power connections on the ECM3 motor. I have another diagram which I made. Let's see. This, I hope, is a little bit easy to understand. Coming into the motor, you have L1 and L2. This is a 120 motor, and it's not an AC motor, it's actually a 250 volt motor. And L1 is connected to one capacitor, which goes to ground. L2 is connected to a second capacitor, goes to ground. So the attempt is to shunt the RFI from the power inputs to the motor precisely at the point of entry to the motor where the power harness is connected. The rest of this doesn't matter. There's some binocular chokes for a voltage doubler circuit and improves the isolation between the two lines. The voltage doubler circuit is jumped only for 120 volt ECM, which mine is. If you jump it for a 240 volt ECM, you will cook the motor and probably your furnace. But the point is, this is a balanced common mode low pass filter. The intent is to shunt RFI to the ground at the motor at the point where the 120 volt lines plug in. Actually, I think one of these is 120 volts and one of them is common and neutral, but the principle is the same. So what did this do? Oh, here's one more diagram. I found that the filter by itself was not sufficient to eliminate the RFI, and I began experimenting. I added a ferrite choke. Initially, I just added a handful of Amazon chokes to the wire harness going to the motor. This is after semi-dismantling my furnace again. And that worked pretty well. But then I started talking to Mike Gruber, and he said, you know, you can make a better choke if you use ferrite material 31, which, given the type of RFI you're getting, will give you a maximum impedance at about 120, about 20 or 30 megahertz, I'm sorry. Is that right? Yeah. This peaks at about 20 to 30 megahertz, depending how you read this. Z is the impedance. This is a ferrite product. You can buy one yourself if you want. It's a choke made of type 31 material. Now, the second thing Mike told me, which most people that work with toroidal chokes know, is that as you increase the number of turns to the choke, the effective impedance increases. So the impedance at 30 megahertz is about 1200 ohms for a 3-turn filter using type 1 material. The impedance when you have multiple turns through a choke is roughly proportional to the square of the number of turns. And now I'm going to show you what finally happened. The first screenshot is with no RFI filtering. You can see these significant lines. The second shot is the same state, no RFI filtering, but I increased the threshold on the spectrum display so the RFI lines are more prominent. Here we are during shutdown, and here we are again. It's just a repeat of the earlier shot. Now, let's look at this again. Here's the spectrum threshold at 5 dB with no filters. Again, this is for the furnace alone. The AC is off. Here's the RFI when the Regal filter is in place. Again, that's a 2-capacitor common mode filter, which attempts to shunt the RFI to ground right at the entry point for the power lines to the ECM motor. Here I tried looking at, I actually took the this filter out, the capacitor filter out, the common mode filter, and I put the RF choke in only. If you compare C with A, you'll see that the ferrite choke filter alone reduced the RFI considerably, comparing A to C, but again, not completely. But interestingly, if you use both together, it pretty much completely suppressed the RFI from the ECM3 blower motor. And that's the arrangement I have now. I have a 3-turn type ferrite type 31 RF choke, followed by this Regal YCAP filter. And I have a very nice RFI-free system. Here I am playing a few games. The furnace is turned off. The furnace is on. I have no idea what this is. This might be from the draft inducer motor, or it might be from the pilot light, something I don't understand. when I turn the furnace off completely, this rather curious line goes away. But you can't have everything, and the perfect is still the enemy of the good. Now I'm going to talk quickly about my second problem. I was getting tremendous RFI from my furnace. Well, the field engineer came out and the dealer sent out a technician, and he said, well, there's no question at all that the RFI is from the inverter. The reason they could tell was they turned on different things independently, including the condenser fan and the compressor. And when they turned on the compressor, I got tremendous RFI. And when they turned it off, it went away. So the first guess on the part of the field engineer was that he should tie up the loose lines for the thermostat. This wasn't just a guess. In the installation instructions for this particular compressor, Lennox tells you explicitly, tie up and remove the extra lines to the thermostat, because the thermostat cable has 4 lines, and I think we only needed 3, has 7 lines, and the 4 unused lines were cut back and removed. This is on the advice of the installation instructions, which says they could cause interference or conduct interference back into the house. And that actually, I was sitting watching the scope on my IC 7300, and that didn't cause very much change. When he added a ferrite choke to the cable, that's the brown cable here, and here, you can see the ferrite choke with 1 turn. That seemed to reduce the RFI considerably. But there was still some interference, and Lennox proposed somewhat vaguely, the field engineer said, well, I could put insulation over the entire T line, the entire thermostat line, or I could try insulating the entire power line going to the compressor. But at this point, this is when the fools rush in hit me, and I said, well, I think I'll take my AC unit apart and see if I can fix it. And in a way I did, in a positive way. I must say, before I did that, I was at a meeting and I was talking to Ron, WA6YOU, and I told Ron that at this point I was sure I had solved my RFI problems. And Ron looked at me skeptically and said, very politely, are you really certain? And I said, yeah, I'm pretty certain. Well, I was fairly new to the club when that happened, and I was relatively new to re-entering the hobby. And since then, I've learned if Ron politely asks you if you're really certain about something, the accurate answer is probably no. And I'll show you why in a minute when I show you some screenshots. But the idea that I had was, Okaya makes filters. They're called Y caps because they open circuit upon overload failure. And these filters are specifically designed for use to reduce noise in electrical systems. And that's a direct quote from the Okaya website, which I think I'll read. A Y capacitor is used in inline bypass applications, typically between the hot line and the ground, or neutral, and ground in North American applications, and between L1 and L2, or L2 in ground in European or other power line applications. So I knew these capacitors were designed to be placed as used as shunts between a lead and ground. And also Steve had used the same capacitor in building the filter for my furnace. So that's why I settled on these filters. I'll discuss the value in a few minutes. This is what I did. I have pictures of it, but I was afraid if somebody tried to imitate the picture, bad things would happen. There are 2 lines coming in. These are 120 lines because it's a 240 system. L1 is black, L2 is white. And this is inside my furnace. L1 and L2 go to a contactor and the control board for the compressor, and the control board is nothing, the contactor is nothing but a solenoid, double solenoid for connecting high power to the compressor circuits. One thing, if you try to do this, no one should try to do this unless they're comfortable. By that I mean you would need to turn the furnace off. You need to reverse the AC safety breaker, which by regulation is very close to the outside furnace unit. Of course, this is an outside furnace unit. And then you need to check to see if any wires are alive using a non-contact voltage probe. Then and only then can you attempt modification like this. But I took my two Y caps, I connected each to a terminal on the contactor, and I connected the other end to a ground lug, which is in the outdoor control board. Rather, it's in a control board in the outdoor unit after you open up the cabinet. These caps open circuit on failure, so they aren't going to destroy anything if they fail. It worked pretty well, and I'll show you that. The advantages are I didn't have to physically modify the control unit chassis. There was a demonstrable reduction in inverter RFI, and another operator tried this and verified on 20 meters that he got a substantial reduction in RFI. And finally, the capacitors are very close to the entry point of the AC wires to the AC unit. And these are all desirable things in the design. There are disadvantages too. There's potential shock hazard because you could have increased leakage current at 60 hertz. You have to be sure that the ground, which is to say the chassis of the control board, is hardwired for safety, and it is. The control board is actually hard grounded by the copper safety wire. The third problem, which anybody who works in RFI design is probably all too familiar with, is the capacitor leads are too long. In any RF circuit, the capacitor leads not only need to be insulated, but they need to be a half-inch less to avoid self-inductance, which can actually shift the self-resonant frequency down. But I couldn't do that. It wasn't physically possible. And by the implementation I did do, I don't think violated my warranty because I didn't cut any lines. This is a hypothetical implementation, which I think might work better, or at least would be more satisfactory. My idea was I could drill 2 holes into the control box chassis, add 2 ground lugs, and then ground each of the capacitors very close to the contactor. The problem here is it might well void the warranty. I also don't like drilling into a chassis when I don't know what's underneath it. And finally, there's a potential shock hazard. I should say shock, but I won't fix it now. And again, you could have 60 hertz leakage to the chassis. So how did it work? After the field engineer from Lennox had done what he had done, disconnected the unused cables in the thermistor harness, and also put a choke on it. When I looked at the RFI from the AC unit, I still had significant RFI, though not nearly as much as before. And this is the RFI after I turned the AC on and I put my low-pass filter in place. That again is just 2 capacitors, which are connected at one end to the contactor on the control board of the outside AC unit, and connected at the other end to a grounding lug on the chassis. That worked very well. I tried using a single capacitor each time. I tried using a capacitor L1, capacitor L2. Neither worked alone. They both had to be in place. They both have to be in place. Okay, that's how I solve my problems. Of course, my problems are very idiosyncratic to my system. What I'm going to try to do now is finish up fairly quickly. And suppose you're buying a new system. The next 4 pages give some suggestions. And of course, they'll be in the handout, which anybody can get a copy of after I finish this presentation. First of all, know the facts. If you're talking to a vendor, you know that high efficiency furnaces are now required by regulation. Find out what's in it. Does the system warranty cover EMI? Ask the vendor if there is EMI. What are they going to do about it? Can they guarantee they can fix it? A really key question is, how many ECMs and or VFDs are in the proposed system? Nowadays, modern systems can have 3 ECMs, one for the condenser fan, one for the blower fan, the furnace, one for the draft inducer fan, the furnace, and finally either a VFD or possibly an ECM. They both have the same problem. In the air conditioner, I know Lennox field techs have told me they run into this, particularly in commercial systems. If you can find out if they say, well, we're going to have to use a high efficiency motor in the furnace, we're required to by regulation, try to find out who the manufacturer is. Ask if there is a kit available for reducing RFI, and ask or insist that it be installed preemptively if there is. You could ask in each case if you want to substitute a non-ECM, that should actually be a non-VFI AC system for an ECM-based system. And here you may wish to consider a 2-stage AC unit, which I'll talk about in a minute, rather than an AC unit with a continuous speed VFD. I have the latter, and I'm going to talk about an alternative. You might also ask if there are any harnesses or cables that need to be shielded. Finally, during installation, insist on the following. Have them turn on the AC unit while you watch the scope. Have them turn on the furnace while you watch the scope. If there is RFI, try to document it, preferably with a screenshot or even with a shot taken on your camera. During installation, you want to write down the manufacturer's model and be sure the user documentation includes schematics and AC electrical wiring, or if not, ask for copies. Here is a safe configuration, RFI safe configuration. In the furnace, you know you're going to have an ECM, but I would try to get one from a manufacturer, Regal being one, but there are many manufacturers that make ECMs, or a combo ECM, and try to get an RFI filter from the manufacturer, not necessarily the alternative manufacturer. I would also insist on getting a non-ECM draft inducer fan motor. There is no reason to have an ECM inducer for the fan motor other than reasons of efficiency. For an external AC unit, I would recommend an AC with a 2-level compressor. If you get an inverter with variable speed compressor drive or an ECM compressor drive, if such thing exists, you're likely to have RFI. And I would get a non-ECM condenser fan. Now, in doing so, you're giving up some degree of efficiency. And a 2-level compressor is not going to have the range of, it won't provide continuous coverage of output. It will give you 2 choices of compressor speeds. Also, be careful about the terminology. You'll notice that a 2-stage gas furnace can still have an ECM blower. A 2-stage gas furnace has a burner which has a high flame and a low flame. But a 2-level compressor has 2 fixed speeds and no inverter. Here again, just know the terminology. ECMs can be called high efficiency DC motors, BDMs, PMSMs. Inverter-based AC compressors can be referred to as VFDs, VSDs, variable capacity compressors. It took me a while to learn the jargon just so I could talk to the field engineers. I'm going to go through these very quickly. Since I'm not getting interference, the furnace or AC is not FCC compliant. That's usually not true. These devices are allowed a small amount of AC EMI, and the EMI can occur just because you've added a wire harness, which serves as an antenna, improper grounding, inadvertent ground loops, or improper wiring installation. Installing an EMI filter will eliminate your problems. Well, an EMI line filter can affect radiated RFI, but not reduce conducted common mode RFI. And there's no FCC requirement to test for radiated EMI below 30 megahertz. EMI filters can protect against both common mode and differential mode, but if the RFI enters a power line prior to the point of insertion of an EMI filter, this filter won't help. And I'm going to give you an example of that. This was a case that Steve solved. He found that if you put a commercial EMI filter outside of the cabinet in which there is an ECM motor, or outside the cage, it won't eliminate the RFI here because it will shunt the RFI from L1 to ground and it will shunt the RFI from L2 to ground. But if the EMI filter is grounded and the cage for the motor is grounded, you can have a return path for the RFI through the AC metal enclosure, or in this case, it might be a furnace metal enclosure. And the RFI will be radiated. Instead, you have to shunt the RFI to ground right here at the adapter plate, which was the whole idea of the RFI filter that I showed you earlier. Not all filters that Steve has to deal with, it turns out, have pluggable filters, or he can't design a pluggable filter for all of them. In some cases, he had to use an EMI filter. And he came up with a very ingenious approach. He figured out a way to build sort of a distributed Faraday shield. This is an ECM. Here's where the connections come in, the control lines and the power lines both. He put a box over the connector for the ECM, took the power lines out through a mesh shielded tube here, took the AC power lines out through a mesh shielded field here. That goes to another aluminum box, which is a Faraday shield for the ECM, for the EMI power line filter. It's a commercial EMI power line filter, like the Schaffner single phase. And finally, the shielded cable exits the cabinet. The key point is that if you completely surround the wiring from the ECM motor, including the power and control lines, to the EMI filter, you can have decent luck, and that can be very effective in shielding RFI. For those of you who don't know what a Faraday cage is, it's just an enclosure used to block electromagnetic fields. A Faraday shield is basically a continuous covering of conductive material. And if you have an external electric field, the charges within the cage, the conducting material composing the cage, the electric charges will be distributed and will cancel the external field. So inside the Faraday shield, you won't have an electric field. Although inside the cabinet, you may well have what Steve calls an RFI soup. Third trope is that adding shielded cables will completely eliminate RFI. That's definitely not necessarily true. A shielded cable can make a great antenna for common mode currents. That's why anybody with an unbalanced antenna, a J-pole and N-fed, will usually have a feed line choke to prevent common mode RFI from traversing the shielded coax. Common mode current can also radiate from the casing of a condenser or blower fan motor, even with proper shielding and grounding, as I showed in a previous diagram. And I've already talked about a couple of remedial measures, including mine, that I use to reduce the RFI from a compressor without additional shielding. My fourth is my favorite. If the RFI isn't fixed, I'll file an FCC complaint. Yeah, you can. But the RFI may be due to local installation procedures rather than component malfeasance. A lot of complaints are simply acknowledged, and the complainant is told that we use for statistical purposes. You can file an informal complaint for free, but a formal complaint costs $225. And finally, the FCC may just refer you to somebody else. After the FCC consulted with local authorities, The ARL was asked for assistance, and they helped the Evanston, Illinois police locate, quote, an errant neon light power supply that was causing widespread RFI all over the city. The FCC originally referred the Evanston police to the Automobile Manufacturers Association because the wireless key fobs in the area had stopped working. A few quick facts. Can you help me select a new HVAC system? No, but I've tried to tell you what questions to ask. Can ferrite chokes alone mitigate RFI? Yes, they can, but ferrites alone may not have sufficient high frequency attenuation. In my case, ferrites had to be combined with a low-pass filter, a low-pass capacitor-based filter. Can you make your own RFI filters? Well, I've given you a schematic, but this filter has only been tested by me on a single Genteq 3.0 motor. Different filters have different harnesses, and you're going to have to match the filter to the harness. And an HVAC dealer or the OEM may be able to advise you whether RFI filters are available for other ECMs. How can I avoid voiding my warranty when I modify my furnace? Well, that's kind of your problem, but there's no generic answer. The HVAC field technician, field engineer from Lennox said, don't cut or reroute existing wires. Don't introduce short circuits. Verify wire by wire that any new plug-in device is compatible with existing wire harness. So the plug-in unit that Steve devised, and which I augmented with a ferrite core, with a ferrite plug-in device, plugged into an existing harness, didn't modify the harness in any way, and plugged in to the existing connections on the ECM. And the modifications I made on my own AC, I did not cut any wires. I just used existing connections. I'm going to finish with a few very quick additional studies. These are people that I helped or Steve helped. KM4CCB, Lennox furnace in the basement was the main source of RFI. He was provided with a filter and ferrite choke and installed it and obtained a significant reduction in RFI. He has 2 Lennox AC units in his second furnace upstairs. They both have fixed speed non-ESM condenser motors and did not appear to be a source of RFI. KC7SE had a Genteq motor, which Steve feels responsible for, but there's no Regal plug-in filter available for it. He provided a kit which provided an extended Faraday shield, I believe, and I already discussed how that works. And this was installed by KC7SE and obtained a very significant reduction in RFI. Here's the RFI without the EMI filter, and here's the RFI with the EMI filter. Well, I want to thank him for sharing those slides. The third example is from somebody who was going to be cited, but did not want to be named or give his call sign. He had dual Lennox furnaces and XC20 AC compressors. He was getting RFI from the LG compressor, as was I. He obtained some mitigation using the YCAP filters I suggested, but they were installed by the dealer, and the dealer wasn't entirely sure he'd installed them correctly. The dealer did install the Regal filter and ferrite kit on the furnace, and that definitely helped. But the bottom line is there was insufficient mitigation of the AC RFI. And what this gentleman did, again, John Doe, was after substantial discussion with Lennox, they agreed to completely replace his XC 4-ton unit with a top-tier 2-stage unit, which is a 2-stage AC unit. Remember, the compressor has 2 speeds, low and high. It does not have a variable frequency inverter. And this completely eliminated AC RFI. And I can tell you from talking to him, my friend was delighted with this. And here's the last quick example. This man had a Regal Genteq blower. As previously, he was given a kit with a filter and a ferrite core. With the RFID filter, the original filter, plus a ferrite core plug-in. And that worked very well. However, he also has a draft induction fan board made by Trane, T-R-A-N-E. He's repeatedly requested assistance from Trane, and there's no response from Trane after 3 attempts, and the furnace is only a 1.5 years old. And I think I'll finish by saying, if anyone from Trane is watching, I certainly would appreciate if they would help VE3PS. I can give you contact information, because these view graphs will be passed around, and I would be delighted to revise it and say that the problems with the Trane fan motor control had been completely fixed. Before we take questions, I want to end up with a quote from Dave Barry. He had a 10 questions air about called Are You a Guy? And I consider in this club to be guyness to be independent of gender, because I think anybody in this club would quickly pass this last question on the test. The print's small, so I'll read it. 1, alien beings from a highly advanced society visit Earth, and you are the first human they encounter. As a token of intergalactic friendship, they present you with a small but incredibly sophisticated device that is capable of curing all disease, providing an infinite supply of clean energy, wiping out hunger and poverty, and permanently eliminating oppression and violence all over the entire Earth. You decide to A, present it to the President of the United States, B, present it to the Secretary General of the United Nations, or C, take it apart. And I assume anybody in this club would take it apart, because we all know we can make it work better. And with that, I will stop screen sharing and try to answer some questions.